Oh, I don't know. I do not. All right. So welcome back from lunch. We're going to have our final kind of specialized lecture before GoCon concludes today. So our last speaker is Steve Yeager. He's primarily an oceanographer. He worked in the oceanography section for a long time, and he is now leading a lot of the Earth system prediction research here. In a second, hang on. Let's try this. Use slideshow. Do you need your notes? Okay, let's try it this way. All right, so he's going to give this last talk, and yeah, these efforts are becoming more and more important to NCAR, I would say.
Thanks, Alice. Yeah, I've got this weird automatic advance here, but I'm going to talk about Earth system prediction. My name's Steve Yeager, and I thought I'd start off slow and simple. I always like talks that start off slow, then I can follow at least part of it.
We're just trying to get the auto advance to not happen.
Super, thanks. So this is a question I ask when I give public lectures, but you know, it's a good question to start things off with. If we can't predict weather beyond 1 to 2 weeks, then how can we say anything about what's going to happen in the next few months, years, or decades? And it's important to understand what we're predicting here. We're not predicting weather. We're trying to use CESM to predict climate. Climate is the statistics of weather, and we can think about it in terms of this kind of simple pinball game where you drop a ball at the top, and you can consider that one weather event. It's very random and stochastic. It's going to land somewhere here in the bottom, and if you do it enough times, you'll build up the statistics of this game. You'll have a Gaussian, basically, of where your ball is going to drop. And that's the climate of the game. So we have extremes, we've got a mean climate, and that all depends on the frequency of where those balls drop in this kind of stochastic event-like sense. But there are things that can influence the statistics of the game. So if you tilt the pinball machine, then you've got a new climate, right? So you drop your balls in, and they're going to tend to cluster over at this end of the extremes. And we can think about climate change in the same way. We've got greenhouse gas emissions. It's changing the statistics of weather. And when we aggregate that over time, over many samples, then we get a change in climate that we can predict. We can't predict where each individual ball is going to drop, but we can predict the statistics of where balls will tend to drop. And so greenhouse gas emissions, of course, are a big influence or a big tilt, provide a big tilt to the climate game. But there are other sort of internal modes of variability in the climate system that also tilt the climate game. So we've got ENSO cycles of warming and cooling sea surface temperatures in the Pacific that can change the climate statistics in particular regions, volcanic eruptions. We've got slow phenomena like changes in the strength of the ocean circulation here in the Atlantic. All of these things are known modes of variability that will change the statistics of climate around the globe. And these are the things we're trying to predict. It's still automatically advancing, by the way, if you could help me out. So let's talk about how do climate predictions work. We basically are going to initialize CESM, or any climate model, from an estimate of the historical Earth system state. And so I'm just representing that schematically here in this simple diagram. So the observations here of some field of the Earth system represented in black here. There's variability over time. Somehow we have a way to reconstruct that state going into the past. And furthermore, we have some way to initialize the climate model from that estimated state. all of that is sweeping a lot of very difficult technical details under the rug of how we go about doing that. But this is the basic idea. Thanks a lot, Alice. That's the basic idea. So we somehow come up with observations in quotes that we can input into the model. And then we run hindcast simulations. These are these red curves here that are starting from the black curve, and we run an ensemble of them. We perturb the initial conditions ever so slightly to produce an ensemble. And you can see the trajectories of each individual member differ from each other, but they sort of track the black curve, sort of go in the same direction, and that's the predictability that we're trying to assess and quantify. So we run these hindcasts, we force them with observed external forcings, and then we repeat steps 1 and 2 many times to generate a collection of hindcasts. So we do this at multiple times, going back into the past. And if we do this enough times, then we get a sense of how skillful the model is, right? And we can see by eye here, this is a pretty skillful prediction system, right? It predicts this downward trend, predicts neutral trend, downward trend here, upward trend here. So we can see by eye that there's skill here, and we would quantify that in terms of skill metrics like an anomaly correlation coefficient to just get a hard quantification of how skillful the prediction system is. So we use, we're now on step 4 here, we use these hindcasts to evaluate model skill at predicting past change. And if we think we have a skillful system, then we produce forecasts, right? We start them from our nearest, or our most real-time estimate of the Earth state. We go forward in time into the future, and we say, this is a forecast. This is what we think might happen. And based on these past hindcasts, we have some quantification of the uncertainty in our forecast, right? That's the basic idea. So initializing the climate model from our best estimate of the historical state, that helps in predicting the internal variability in the climate system. And when we use observed or projected external forcings, then that helps in predicting forced variability and change. So we're getting both elements, internal variability and forced variability, kind of represented in our prediction system. And so you've probably heard about uninitialized or projection runs. We've got 2 types of prediction systems now with CESM. We've got projections into the future that are just based on scenarios of what future forcing might look like, and also observations of what the past forcings were. And in particular, an example of this is the CESM large ensemble. Both CESM 1 and 2 have these large ensemble simulations that weren't exactly uninitialized. They were just initialized so far back in the past that all memory of the initial conditions has faded in these simulations, and all the variability is then coming from the external forcing. As you can see in the top right plot here, the external forcing driving this very pronounced warming into the future. And for these simulations, we expect skill for long time scales and large spatial scales. And what I've been describing is an initialized prediction system. And an example of this is the CESM Decadal Prediction large ensemble, which I'll talk about in a few slides. And in this type of system, the skill is coming from both forced and internal components. So we've got the internal variability coming through the initial conditions that we start the model from, but we're also applying the forced changes, the changes in greenhouse gases and solar radiation and whatnot. And so in an initialized system, we expect better skill for short time scales and small spatial scales. And so just getting into sort of what we do in this space with CESM, we founded a working group back in 2020 to coordinate initialized prediction across the CESM community. And the idea is that this Earth System Prediction Working Group provides a nexus for research into origins, mechanisms, and limits of Earth system predictability, the fidelity of coupled model behavior, because you can directly compare the coupled model to observations, and the potential to deliver reliable, actionable, advanced warning of near-term regional environmental change. And this schematic here kind of illustrates where we think initialized prediction with CESM is most relevant. In between the pure initial value problem of weather prediction here on the far left, where you're just initializing a model to try to predict what's going to happen in the next few days to week or two. And on the far right is the boundary value problem, where you're just running a model with your estimate of future forcings to look at century timescale changes in the Earth system. And in between those two extremes, sort of both matter, both initialization and forcing matter. We're in this regime here where, on timescales from, say, months to decades, we need to initialize the model, but we also have to force it. And so we kind of conceptually split the space into three foci, I guess: subseasonal to seasonal, or S2S, seasonal to interannual, and then seasonal to decadal timescales. And you can see the schematic here shows the kind of modes of variability that we think are going to contribute predictability on these different timescales. So, for example, on decadal timescales, we really care about initializing the ocean. The ocean is going to be the source of memory. Whereas on subseasonal timescales, maybe the ocean doesn't matter as much. We really care about things like, the MJO and the NAO in the atmosphere. So we have to initialize the atmosphere and the land. And then I'm just going to go through and kind of give you some examples of work that's been done on these different timescales. So S2S Prediction, we've done with CESM2. The experiment design looks like this. We initialize the model every week over a time span from about 1999 to 2020. We run the model for 45 days, and we use a 10-member ensemble. So this kind of experiment is about 2,000 simulation years using CESM2. And you can read about it in this paper that Yaga Richter led in 2022. And I'll just show you some example results from the CESM2 S2S system. So here on the upper left here, you can see the 2-meter temperature skill score. This is anomaly correlation coefficient. So the higher, the closer to 1, the better the skill. And you can see that the skill goes down with lead time. So in the first 2 weeks, you're getting pretty high correlations for wintertime predictions of temperature over global land. And then weeks 3 and 4, the skill drops and kind of asymptotes at weeks 5 and 6 at a low level. And you can compare how CESM gauges up against ECMWF, which is the European system, or CFS, which is NOAA's subseasonal forecast system. So CESM is actually doing pretty good compared to these more operational centers. And then on the right, you can kind of get a visual sense of where the skill exists at early lead times, and then how it dissipates as you go further and further forward in the forecast. We also have produced a seasonal to interannual prediction system. We call this SMILE, for seasonal to multi-year large ensemble. So we did this with CESM2 just last year. The paper came out. And here it's the same idea. We're initializing a bunch of hindcasts, but now we're initializing them quarterly rather than weekly. So every 3 months we initialize a set of hindcasts spanning a longer kind of time window from 1958 to 2020, and we run these simulations for 24 months rather than just a few weeks. So we're trying to get out 2 years into the future. How much can we predict? And this experiment is more expensive at 10,000 simulation years. But with this type of experiment, we can ask how well can we predict ENSO, which is a key source of seasonal variability in the climate system, and also a key source of prediction skill on those timescales. So if you look on the right here, you can see the DJF Nino 3-4 index from observations in black. And then the various colored curves show our predictions at various lead times. So the one up here in panel A is initializing in November and trying to predict the subsequent DJF Nino 3-4, and you can see the skill is very high. If we initialize in November, correlation very close to 1, and you can see by eye how good this is. And as you go further back in time, say you initialize in May and you're trying to predict DJF Nino, then your skill drops, right? Now the ACC is only 0.8. You can see by eye areas where we missed the forecast, and so on and so forth. This is a pretty interesting experiment. It's sort of the first time we've put CESM through its paces in terms of seasonal prediction of ENSO, and we're pretty pleased to see that our system, which is in blue here, has skill that is very comparable to sort of the leading seasonal prediction data set, the North American Multi-Model Ensemble here in red. So we're kind of right on top of that. And we're not much worse than ECMWF, which is shown in green here. So, we've got a system using CESM that is comparable to other leading ENSO prediction systems. So this is a really powerful tool for doing science and understanding how ENSO works, how we might be able to predict it better, etc. Just another plot from SMILE here, again showing skill as a function of lead time. So this is lead month 1, 4, going down as you go down the plot here, and you can see the correlation scores dropping. So this is the skill for seasonal temperature, and you can see it's pretty good. Even out to lead month 10, you can see we're able to predict variability in the tropical Pacific, which is pretty important for global seasonal climate. However, if we look at the corresponding seasonal precipitation skill, it's much lower. And so why is that? We're able to predict ENSO, but we're not able to predict precipitation over land. And so this is an outstanding science question. Why is the model unable to simulate these teleconnections from the tropical Pacific to climate over land, and what can we do to improve that? That's kind of a key research area right now. And finally, just touch on this final long time scale prediction framework. Decadal prediction, this is still remains our leading decadal prediction system using CESM. It was with CESM1, and we did this back in 2018. So for decadal prediction, we're initializing less frequently, only once per year. We're running out longer, 10-year simulations, and we use a larger ensemble size. So all told, that is a much more expensive experiment than any of the other prediction systems. So it's a very significant resource ask to be able to complete one of these experiments, 27,000 simulation years. But this is the sort of thing that we can do if we do have those resources. So we can look at skill for things like summertime precipitation at the first 5 years of the prediction, the years 3 through 7 and years 5 through 9. And again, I'm showing you maps of correlation skill. So where you see red, it means the system is doing pretty well. And what really pops out here is if you're trying to predict kind of pentadal precipitation changes in summertime, it turns out we've got really high skill in the Sahel region of Africa and also parts of Northern Europe, kind of at these mid-range lead times. And we can ask how much of that came from initialization as opposed to forcing, right? I mean, do we really need to initialize the model, or can we just get away with using external forcing? And it turns out for this particular quantity, the initialization is really important. So a lot of the skill that we're getting in North Africa is coming from initializing the ocean component that has memory that changes basically the position of the ITCZ that that governs rainfall variability in summertime over this part of Africa. So this is a really encouraging result. And here I'll just kind of show you what that looks like in terms of a time series. So here is a regional average over the Sahel region of Africa for summertime, and the observations are in black here. Red is the Decadal Prediction large ensemble, and then blue is the CESM uninitialized large ensemble. And you can see the variability is much reduced in the model simulations compared to observations. But if you renormalize, then all of a sudden you see the prediction system in red is tracking observations really well. And it suggests that we could have predicted the drought of the 1980s in the Sahel region if we had had this system back then. So this is the sort of, prediction of climate statistics years in advance that we think is really exciting and potentially useful to society. We can do it when we initialize, but if we don't initialize, then we get what's in blue, and you can see that we're just not getting skill there. So we need to initialize the model to achieve this type of skill. All right, that's kind of my spiel. If you're interested, I encourage you to get involved in the Earth System Prediction Working Group. Go to the website, sign up for the mailing list. You'll be notified whenever we have meetings, which is twice a year, once in summer, once in winter. Or you can send an email to one of the co-chairs, me, Yaga Richter, or Kathy Pajon. Thanks.
All right, thank you, Steve. So who has some questions about this?
Thank you for the nice talk. I have two questions. First is a very general question, is about from the perspective of predictability. How do you think about the AI vs the physical model from different time scale, especially the sub-seasonal to seasonal time scale, which is hard to predict, and also for the time scale larger than decadal time scale?
What type of model did you say?
I mean, AI model vs the physical model, like our system model.
Yeah, that's a good question. I mean, there's more and more sort of AI prediction work coming out. I think it's exciting. I'm not involved in any of it, so I still tend to think of it as a black box, and I'm more interested in physical understanding. So that's where my hesitation comes from. I think it's harder to generate real physical understanding of mechanisms using an AI prediction model. Okay. Maybe there's a way, explainable AI, but I feel like just using a dynamical model, you're able to do experiments that kind of shed light on where skill is coming from. And so that's the sort of thing, once we have these foundational hindcast data sets, then other people can come in and do sensitivity experiments. Like, okay, what happens if we withhold information from the North Atlantic? Does our skill disappear? And that's how you generate knowledge of where predictability is really coming from in the Earth system.
My understanding is that for the AI model, they kind of do the attribution study. Like for physical process-based model, it can do it very well. So I think maybe it's our advantage currently.
Yeah.
Yeah. And another question is about the decadal timescale prediction. How do you think about something like PDO and its impact on the extreme events over lands? So can model capture them very well? Because the PDO is kind of several decades since.
Yeah, I didn't put in a plot for our. I'd left that out. I usually show a plot of surface temperature skill on decadal timescales, and what you see is the North Atlantic is a hot spot of predictability because we've got AMOC there, and the Pacific is kind of like a cold zone where we're really not predicting well on decadal timescale. So I think there's potential, and I think maybe the model is showing low predictability in the Pacific due to model error. So we've got a paper out showing that actually the model response to volcanic forcing is something that degrades the skill, which shouldn't be the case. So there's potential there to improve skill in the Pacific, but right now I would say most decadal systems do pretty poorly in the Pacific and for the IPO and PDO together.
Yes, hi. I had a question on your S2L slide. I was wondering, it had the, yes, this one. I noticed in 1980, it seemed like at a bunch of lead times, CESM really wanted to force a somewhat strong El Nino, like a 13 months, 16 months, 19 months. It seems like one of the most sort of notable failure modes, or at least failure examples.
Yeah.
Are you familiar with why it's such a disconnect between what happened and what the CSM wanted to happen?
Yeah, that's a great question and very astute observation. I suspect this is related to initialization shock. We had a really severe problem with that in CESM1, where all of the hindcasts initialized kind of in the first half here tended to produce a very strong ENSO in year 2. And we were like, why does that happen? And then the later ones would tend to produce La Nina. So you kind of have this downward trend. And that was traced back to an error or a bias in the initial conditions where we just had a too strong zonal SST gradient, unrealistically strong in the early years. And so you had this spuriously strong Bjerknes feedback that gave you this ENSO response. It's like a shock coming from that too strong gradient. And I suspect we've still got a remnant of that in this system where the model is sort of trying to produce an ENSO kind of at lead times, I don't know, 10 to 16 maybe. And we just haven't nailed the initial conditions kind of that far back. As we go back in time, of course, our initial conditions are less reliable because we've got less data constraining our reconstruction. And so that's one of the challenges in this game is how do we get really high quality initial conditions going far back in time.
Hi, Steve. Thanks for your presentations. My question is related to one slide where you mentioned the observations in the framework of your predictions. And my question is, do you think of or have you thought of how much observations is needed to improve the model skill and any sort of criteria for like future projects to like set up observations in favor of improving model skill?
Well, I mean, that's sort of following on from the answer I just gave, right? This is one of the major challenges, particularly for decadal prediction. You know, if we go back to the sub-seasonal timescale, you know, we're only going back to 1999, and we've got, even in the ocean, pretty good coverage back to 2000 when we have all these Argo floats that came to sample the ocean. So, you know, if we're doing S2S, it's less of an issue, and maybe the answer for S2S is put all your money in data assimilation, right? I mean, that's what you need to improve weather forecasting. You just need data assimilation. You need as much data as possible to constrain your initial conditions. I would say that's answer is less applicable for these longer time scales, right? Because in order to assess a decadal prediction system, we need to be talking about decadal modes of variability, like AMV, PDV, right? These are decadal modes, and so we need a long time span to assess skill at predicting those modes, right? So we've got to get back into the mid-20th century, and how do you do that? I mean, I don't know that data assimilation is really going to help get us further back with higher quality. The way that we do it is we force the ocean model with atmospheric reanalysis. So most of the observations, you know, in the mid-20th century are atmospheric observations. So just leverage those and force the ocean model with atmospheric reanalysis. And that seems to work for us. And so I think the answer is, developing better ocean state reconstructions that, I don't know, are probably some compromise between data assimilation and just purely atmospheric forced simulations.
Thank you for the excellent presentation. So I have a question. It's about the the way we actually improve our understanding of the different kind of teleconnection methods is by looking into the hindcasts. So I understand that it's sort of like creating a composite of like same kind of meteorological process, and then try to understand what was going on, what was the state of the atmosphere. So NVIDIA, they are currently working on a pattern recognition based weather forecasting system called ForecastNet. So in principle, they are using the neural network to actually do the same thing. So in your opinions, like what are the things that you think should be, it's like we should be watching for to, for methods like them? It's like, well, what should be we should be considering to being guided and not misguided by the AIs?
That was a hard question. So like what sort of precursors should they like be weighting especially highly? Is that like, I mean, I don't know. I don't know. But I would say that I'll just give, kind of sidestep that question and say that, I think one of the real benefits of doing dynamical prediction, this is getting back to an earlier question rather than AI-based, is that we learn stuff about the model when we do this. And I don't know that we're going to learn about the model if we just use AI to get the best forecast that we can, right? That doesn't feed back to model development, whereas this exercise does, because it tells us, is your model, like I said, is your model like completely screwing up the response to volcanic eruptions? Like you're not going to know that in an uninitialized framework, because you're just going to look at global surface temperature. You're going to say, yeah, it dipped. We got it right. But if you do it in an initialized framework, you'll see, hey, the skill just went down when we added more information to the system. That shouldn't happen. So something's wrong with the model that we need to fix. Like that is really kind of the stuff that gets me excited. It's like this helps us build a better model.
All right, we'll do one last question here.
Thank you, Steve. Your presentation helped raise a number of interesting questions. So I was interested about your
Let's
slide.
stick to one for now, and then maybe you can talk to him after, just so that we stay on time for the challenge exercises.
So you mentioned like there are skill comes from two set of experiments. One is uninitialized, another is initialized. In the case of uninitialized, you say that the skill comes from correctly simulating the forced variability and change. So how do you assess that it is actually correctly simulating the forced variability? Because if you are studying the forced response, so even we know like due to the changing background conditions, background climate, even the forced response would also be changing. So how do we assess the correctness of the simulations in those cases?
I didn't quite follow the question. Sorry.
Yeah, this one.
So yeah, we've got two kind of approaches that kind of use different sources of information. So just pure forcing versus forcing plus internal variability. And the question is, how do we determine what?
So how do we assess that the skill comes from correctly simulating the forced variability? So because when we are simulating, trying to assess the forced response, so there is also the background climate change. So how do we assess the correctness of the simulation?
Yeah.
It is
so
purely due to the
I'm-
forced response.
Yeah, so what we can do is we can do this initialized experiment and then withhold some of the forcing. And if your skill drops, that's what you would expect, right? You're withholding information and your skill goes down. But if you withhold information and your skill goes up, that's what I was saying. Then that tells you something.
Okay.
That tells you, well, by adding that forcing, the model response is becoming less realistic. Why? That's the sort of sensitivity experiment that you can do once you have kind of a base set, which we already have. So you guys can go off and do all kinds of sensitivity experiments, like what happens if we redo decadal prediction, but we take away solar forcing, like the solar cycle. Does it matter? Maybe it doesn't matter. That tells you something. And that's how you go about it.
Thanks.
Great. Thank you so much, Steve. So as he said, if you're interested in using these experiments or learning more about the Earth system prediction, join the working group or get in touch with them. So thank you so much. All right. Okay, so where are we at now? We have we just had our lecture here, and whoops, I'm not trying to move that. And now we're going to go into the first set of challenge, or into the challenge exercises. There are going to be some intros, partially in the breakout rooms, but I'm going to give an overall comment in a minute. So I wanted to point out that I got that show of hands earlier this week, who wants to do which component. So we want you to start with one component. There are a number of exercises for each, so you may not finish them all today, and that's okay. You should go your own pace through the challenge exercises, and especially if you have an account on Cheyenne, you could do them later, or if our accounts extend past this week, you might be able to do them next week too. So if you're interested in the atmosphere, so CAM, Chem, or WACM, you're going to start in here and get an introduction from Cecile, and then I think you guys might move to the library, but I'll let Cecile drive that train. If you're interested in the ocean or sea ice, we're going to go to the Chapman room. I'll show a map in a minute here. If you're interested in the land, you're going to go to the Damon room with Peter here, so he can help you get there. And then if you're interested in land ice, you're going to go to the director's conference room. So here's the map. Don't get up and leave yet, because I'm going to show you one other thing. So just to point out, if you're the atmosphere, you're going to start here, of course, and then you'll go up to the library, probably when you're done. If you're going to do the land, you're going to go up the stairs and then into the Damon room. If you're doing ocean or sea ice, up the stairs and then kind of past the library into the Chapman room right here. And then land ice is up the stairs and to the left into the director's conference room here. So that's where you're going. If you don't know which one of those, if you still have questions, come find me. I think there are a number of people I've seen come in, so I can start directing you to where you need to go. And then the other thing I just wanted to point out is that, as you are all aware, we broke Jupiter yesterday. But we have been told that it is working again. So we're going to give this, I'm going to follow Jesse's footsteps. This may be horribly embarrassing. We'll see. So what we're going to recommend is that you start with the challenge exercises, but you're running simulations, so there'll be some downtime while you're waiting for the simulations to run. And we do have a reservation today as well. So actually, let me change how I did this. So I'll open this here. And we had, under resources, HPC environment, there is a reservation code here that should already be active that you should be able to use until 5 today. So hopefully our simulations will go through pretty quickly. But while you're waiting for things to run, you could try to do the diagnostics exercise. So let me try to log in here. It's thinking. And I think the key is that we all don't log in at the same time. And so, if we're kind of doing it at the pace that we get to the point where we're ready to go, then it should be fine, is what Sizzle has told us. And if it's not, I am so sorry, but I don't know how to fix that still. And we can try the tunneling, and we'll kind of deal with it as it comes. So let me see if this lets me log in. My duo seems to be working today now. Hopefully. Okay, so here's where I think Jesse kind of, we got stuck yesterday, so let's give it a try. I'm going to start a session. I might have already had a session open, so we'll see if it makes me select resources. All right, so you get here, you're going to go to Casper PBS batch. The account is the UESM 0012. You're just running on Casper, so we don't have a reservation today, but Casper is usually quick, so you shouldn't worry about it. You can give yourself a longer wall time than 2 hours if you would like. Then we're going to launch server, and here's the real test right here, right? Yay! Okay, so that blue bar went, and it's opening. And I have more stuff in my home directory than you will. So you should have downloaded CESM tutorial just straight into your home. I had put it under a directory called workshops, but you'll click on it, and then you go into notebooks and into diagnostics, and I'm going to go into SICE because that's what I know best. And I click on SICE, and what you'll see is now it automatically populates the environment you need. And so then you can run this cell either by pushing that arrow button at the top, and you watch this little asterisk, and then when it goes to 1, it means it ran. Or instead of pushing the arrow button at the top, I'm gonna, again, you put your username in here if you wanna look at your data, and you should be able to look at this, use this to look at today's data. If you need, you'll need to be careful of the simulation name, and so here it's preset to b.day 2.1, and it's also set here, so you just might need to be careful there, but I'm just gonna point to the existing data, and you can also run by pushing shift, holding shift and then pushing enter. You can see it's doing its little asterisk, and then it will go to number 2 when it's ready. So there we go, so it's loaded the data. So it does seem to be working, so just kind of, go on in batches, and it should work. It's just we all hit the system at once, and then it freaked out, and they have learned something now, I think, from that too. So hopefully you'll be able to kind of do yesterday's at the same time as today's. We have you still broken up by disciplines, sort of, by the different components. So, if you're running the SICE challenge exercise and you're running the SICE diagnostics, hopefully the people in that room can help you with both. So are there any other questions before we start to kind of split up into our groups? No, okay. So Peter, come up to the front. If you want to do the land exercises, go ahead, get up and follow Peter out. I'm going to just kind of do this in little groups. And I'm going to log out so no one else is using my thing. Thank you. Sorry, I didn't come grab it. I guess I didn't say we're going to come back here also, and I'll make sure to come tell that other room, but we'll be back in here. We want to start right at 3:45, so at 3:30 I'll come around and start collecting everyone. Okay, so if you're in the sea ice, ocean, or land ice groups, you want to run that, you're going to come with me, and then everyone else stay in here, and the land or the atmosphere folks will be in here.
Minute? Yeah.
Do you want me to say something about
Sorry?
I can say something about chemistry exercises.
Yeah. Yeah, then it's very brief because I want you to have enough time if possible to do this exercise. Then today, this group is going to do the CAM challenge exercise, and we will move to the library after there. It will be our spot. And Rebecca will be here to help you with the chemistry exercise if you are interested in chemistry. Don't ask me any question about chemistry. You would be very disappointed. And I don't know who else is helping. Ben, okay, then we will, you will see us there. Okay, then what we are going to do, and this is for CAM, but it's going to be the same kind of idea for the chemistry. Then instead of running a FCOM set while you have been running so far, a FCOM set is when you have all the components of the model active. You are going to run a FCOM set, and a FCOM set, you are going to use data for the ocean, sea surface temperature that are coming from observation, and also data from the sea ice. You will have the sea ice extent that would be determined by a data set. And it's what we call the FCOM set. And you will go through the lesson today, and they will explain you some of the difference between the FCOM set and the FCOM set. And basically, it's what I was showing yesterday. I'm going to spend very little time here because I want you to move on this on your own, and it's how you will be learning. Then what you are going to do today, I was very ambitious. You have 6 exercises in 2 hours. Good luck. You don't have to do the 6 exercises. Then this is the CAM challenge exercise, CAM, and you have 6 exercises over here. And for CAM and WACAM, under this, you will have other exercise if you are not doing the atmosphere model. And then this is the list of the exercise, and I have 2 number 4, I will fix this. Basically, you go like the previous day, you go step by step into the chapter of challenge exercise or the CAM or the WACAM one. And then for CAM, I want you to do the control case. It's a FCOM set. And it will be explained what's a FCOM. And after, you try to do at least one of the exercises that you compare to the control. Okay? And maybe do you want to say something now about CAM?
Yeah, I can say a couple of things. So in the chemistry, there's 3 exercises. One will be like the control exercise, and then you will change chemistry in the second exercise, and then you will change emissions in the third one. And the changing emissions is actually quite complicated. So that's actually an advanced challenge exercise. So there's 3, and then there's a 4th option of visualization with a geov tool as well. And so I think that's the exercises we have planned.
That's great, yeah. And we will be in the room. And are you helping for WACAM or for CAM?
So
is there anybody doing WACAM in the room?
So we have WACAM and CAM.
Then this is these 2 people. Then.
So Ben and also Jun is also helping. So we have 2 helpers as well for chemistry.
Perfect. And then last thing, we talked about this before. I have put here the name. Then don't forget, if you want to set the tutorial queue, it's available, it looks like, until 5. Then if you want to use this queue, you change it with this number. You can find the number in the resources, the HPC environment. At any other time, or if you are getting close to 5, don't use that queue because your job will die at 5. Then you use the regular queue. I think they will leave the website, the account for a little bit longer that you can continue to do some exercise. This is it. Then if you have any question, otherwise we can even keep the question because I don't want, if you have a very general question that's for everybody, you can ask, but otherwise let's move to the room and ask library and ask your question over there because we want really you to have as much time as possible to run this, okay?
Okay, so welcome back. I believe that from my running around to the rooms that it went a lot smoother today. Is that accurate? Yeah, there are a lot of smiles. Okay. That's good. All right, so we're not going to do a recap of the lab right now. We're going to have a final presentation. So this is kind of a wrap-up. As soon as GoCon's done, I'll just have a few final words. And then you will officially be done with the CESM tutorial. So this final presentation, it's going to be by the current CESM chief scientist, Gökhan Danbosoglu. He's in the oceans section as well, and he's done a whole lot of ocean model development, won the CESM Distinguished Achievement Award, and has been CESM chief scientist for a long time, and I think he's ready to take that hat off pretty soon. So thank you for being here, Gökhan.
Thank you. Well, this was supposed to be a Monday morning talk when the whole thing started, and I got stuck in London, Heathrow Airport, and I had to stay there overnight, coming back from vacation from Turkey. So anyway, what I try to do here is I try to modify my talk so that it's going to be sort of a recap rather than an introduction to CESM. But before I start, I just wanted to remind everybody that I know that many of you are asking questions about computer time, whether you can keep it or not. So we'll try to make sure that you can keep your accounts. But I just want to also make sure that you know, if you are a graduate student at a US university, then you can automatically get at least 200,000 hours on Cheyenne just by going to the CESL website, and your advisor may need to approve it, but that's already there. And NSF actually provides that support to all the graduate students or early career faculty members and all that stuff. So you don't have to necessarily rely on the computer time that you get through this workshop. So that's something to keep in mind. I think you just go to the CESL website, and there's a web page or something you just fill out, and you automatically get, I think, access to all the computer resources up in Wyoming. So anyway, well, I'm glad that everybody has enjoyed the CESM workshop, and at least that's the report that I received, besides maybe some hiccups on the computer side. So what I'll try to do here is, just as I said, recap some of the CESM highlights and capabilities, and I'll try to sort of briefly summarize where we are going in the future. Probably you have seen or you have worked with CESM2, and I just wanted to highlight some of the things that we are planning for the next version of CESM, that'll be CESM3. Before doing that, however, Alice asked me to sort of stress what CESM is all about. We are all about community. I mean, the CSM stands for C in CSM is the community, and we take it very seriously. This is sort of the schematic of our governance structure. As of now, we have 12 working groups. About 5 or 6 of them are actually 7 of them are model development working groups, such as the atmospheric model working group, ocean model working group, land ice working group. But we have also application working groups, such as climate variability and change, Earth system prediction working group. All of these working groups have at least one internal, meaning NCAR, from NCAR, and one external co-chair. And all of the sort of what CESM does, its priorities and all that stuff, are determined by discussions that happen within the working groups. We have the CESM Scientific Steering Committee, which oversees essentially all of the activities, determines priorities for CESM in consultation with the working group co-chairs. And then we have our advisory board. The advisory board is completely external. And during my tenure as the chief scientist, I switched sort of the composition of the scientific steering committee from 50-50 NCAR, 50 NCAR versus external. It's pretty much, except myself and the CGD lab director, now it's all external, all of the SSC members. And as you probably heard, we have been doing this coupled modeling, community Earth system modeling, for about 30 years now. And CESM is the only community based Earth system model in the world. We have our annual workshops and working group meetings, and we just had our annual workshop back in mid-June. When they were virtual, we had about 700 participants. When they're in person, usually we get about 300 to 400 participants. Each working group has one of their meetings at the annual workshop, but working groups also have their regular sort of extended meetings during the winter time. They can range from December all the way to February. So if you're interested in essentially attending, and we are here to help you to make sure that you attend if you are interested into those in working groups. And if you have an idea to pitch, and if you want that idea to be sort of incorporated in CESM, we can work together. You can pitch those ideas at working group level, and then they trickle up or bubble up, I guess, so that they become priorities. In addition to working groups, this is one of the examples. We have annual CSM tutorials, and you know all about that. But in addition to this more sort of 5-day-long tutorials, we do have shorter half-day to one-day tutorials at AMS, at AGU, and this year also Brian and a few others are leading another effort to have CSM tutorials in Kigali, that's in Rwanda, in association with the WCRP, that's the World Climate Research Program Open Science Conference. So we are essentially, it's not just national CSM, it's quite a bit international. We have a lot of international collaborations, and this is going to be our first effort reaching out to global south. So with that, I'll just talk about some of the capabilities. It's a recap. And I'm not sure whether anybody introduced you to the CSM strategic plan. If you are interested in what our plans are for the next 5 years or so, we have the new CSM Science and Strategic Plan available. It was released in March 2023, and it provides a roadmap as detailing our priorities over the next 5 years or so. And you can find that strategic plan, a PDF version of it, at this website. It is essentially, it's based on input that we received from the community. It goes back all the way to 2019 summer workshop. We received quite a lot of input, and it is determined by the community's priorities, emerging science topics that came about, and then the final version includes many additional updates as well. And our guiding principle is, of course, advanced science and understanding of the Earth system, and provide actionable information for societal use at relevant temporal and spatial scales. I'm talking about from our coarse resolution model version all the way to, I'll briefly mention, our planned ultra-high resolution activities. One of our sort of newer efforts is actionable science and climate justice. In order to we recognize the importance of this activity, and we, back in last year, it's not that far back, at our annual CSM workshop, we had 2 cross-working group sessions on justice and climate change and actionable science. As a result of those discussions, and after discussions with the SSC, we formed a task team on climate and environmental justice. And Monica, who's here back there, is leading that task team. But I just wanted to pitch this here. Within NCAR right now, we don't have the expertise to sort of do reasonable progress or have reasonable progress on these activities. We are heavily relying on, or we will heavily rely on, external community participation, because internally at NCAR at the moment, we don't have the expertise for actionable environmental or climate justice related sciences. So that's going to be an important effort, and as a first step, we are planning to have a workshop I was saying that we should probably have it in the fall, but we need to get our ducks in order in terms of funding, so that may be delayed. I don't know, maybe early spring or something. But if you're interested in these activities, and I think Monica already mentioned this thing. In fact, we were just well, she was actually talking about forming a sort of an email alias. And that'll be formed, hopefully by early next week, so that you can sign up and subscribe to that email list. And since this is a recap, and you probably went over all of these and used simulation results, I just wanted to briefly summarize what's available and what where you can find those. Many of the exercises you performed were based on CESM2, and as this is now has been out, CESM2 has been out there since over the last 3-4 years, and you can find many of the sort of CSM-related publications in an AGU special issue that was finished, I think, back in 2020 or 2021. There are roughly 50 manuscripts available, and if you have any questions about a component model or how the CSM simulations are performing, you can always actually go back to that CSM publication site, and then you can have easy access to EGU publications. And you probably also heard about CSM2 large ensembles, and this was a collaboration with between CESM and Institute for Basic Science, Center for Climate Physics, that's in short ICCP, in Busan, South Korea. Indeed, we ran all the simulations in South Korea for this effort, and it was a very nice, fruitful collaboration. We ended up producing 100 ensemble members. This is our at nominal sort of 1 degree horizontal resolution. All the data sets are again available. Probably you heard about it. And I just put down the primary manuscript that you can refer to for these simulations. As a spin-up or spin-off of that, we also performed single forcing large ensembles. And these simulations were done at NCAR in Wyoming. We performed 4 ensembles of the following set: greenhouse gases only, anthropogenic aerosols only, biomass burning aerosols only, and everything else experiments, and each set contained 15 ensemble members. And all these data sets are available as well, and this effort and the manuscript was led by Isla Simpson, and that's accepted for publication just literally a month or 2 ago. So that's also available. Probably you can find it in early release in Journal of Climate. And this is an interesting study because I don't know whether you are familiar with these ensemble single forcing or impacts of forcing different forcing elements. What we are showing here is that whether you do greenhouse gases only, for example, versus everything else is changing, but holding greenhouse gases can change the results significantly. I'm not sure whether Isla actually talked about that or not. So that's an important, actually, scientific result, and it essentially puts the future experiments of this kind into question, essentially, which way is the right way. I don't know whether there's a right way or wrong way or not. Another thing that I wanted to touch on is our high and ultra-high resolution efforts. When I say nominal resolution, our workhorse configuration, I usually refer to nominal 1 degree horizontal resolution. And when I say high resolution, I'm using 1/4 degree atmospheric model and 1/10 of a degree ocean model as the high-res version of CESM that already exists based on an earlier version of the model. And when I say ultra-high resolution, I'm talking about resolutions of 5 kilometers or finer. And that's, I mean, this distinction is sort of arbitrary. This is my version of defining these. And we do have an unprecedented, what I call, set of high-resolution simulations listed up here. And all of these are, again, available on CESM websites. These results were obtained as a collaboration between Texas A&M University, us, and Qingdao National Laboratory for Marine Science and Technology. because of political reasons, that got shut down. So we don't, that collaboration is down the drain now, but we are collaborating between Texas A&M and us, essentially, to continue this line of work. Some of these simulations were actually run on Chinese machines, on exascale computing, and that's part of the reason that this project got shut down. So anyway, it provides essentially quite important high-resolution simulations. I mean, these are the first of a kind in the world. We have order 650-year pre-industrial control, 3 ensemble members of the historical, and then it's RCP future transients. And then we also managed to run 5 cycles of the ocean sea ice coupled force simulations. And this model version is based on CESM 1.3, and it is being continued to use. It'll be used on retro to perform some paleoclimate simulations, for example. And I'm happy to report that we just got funded about a month or 2 ago to extend these simulations. Indeed, we'll be expanding to add more ensemble members for the historical and transient. We are going to increase the ensemble size from 3 members to 10 members. We will be performing additional RCP simulations. We are using these results also for regional downscaling purposes. We do have a version of CESM, regional, and embedded versions of CESM. Officially, we are not supporting them here, but they are supported by Texas A&M University. And if you are interested in downscaling purposes or embedded versions of CESM, they are available from Texas A&M. And again, we are using it for example, ourselves for actionable or societally relevant science, focusing on, for example, Gulf of Mexico, sea level rise, sea turtle habitats associated with sea level rise and the warming of the SSTs. Another extension of this high resolution thing that you may be interested in if you're interested in ocean biogeochemistry, we do have forced ocean simulations with ocean biogeochemistry also available with this model version. This is forced with our, I would say, best observed, best atmospheric reanalysis product for 1958-2021 period. We also expanded, I think Keith may have talked about this, we have now an expanded enhanced version of MARBLE. MARBLE stands for Marine Biogeochemistry Library for the ocean model, biogeochemistry, and we are using it in conjunction with the fish model. Well, I shouldn't say the fish model, it's an fish model. It's FISTI, Fisheries Size and Functional Type Model. We are using it in combination with our Earth System predictions to predict fisheries, essentially, species and how they are going to change with changing climate. And recently, though, we have been expanding this effort. Now we are getting into the ultra-high resolution version of the model. We have a collaboration with Texas A&M and University of Michigan, along with 3 NCAR labs, including CGD, to create a non-hydrostatic version of the spectral element atmospheric dynamical core. And this is also in collaboration with Department of Energy. We are planning to essentially transport or transfer their non-hydrostatic version of the spectral element model as part of within the CEMA framework. I don't know whether anybody mentioned the CEMA. Okay, so I'm not going to say anything about this. I'm sure I wasn't here on Monday morning, maybe, anyway. So you can ask me about what CEMA is, or you can ask Brian what CEMA is. CEMA stands for System for Integrated Modeling of the Atmosphere. And it's an effort within NCAR to unify the atmospheric modeling framework, including dynamical cores, chemistry, and physics. So this is going to, one advantage of this thing is essentially, we are, as you may have heard, our new machine Dretro, which is on the floor right now, has a GPU side. And as our current code cannot take advantage of GPU side as is, or efficiently, I should say. So the idea here is essentially DOE version has a C++ version of the spectral element non-hydrostatic core. So by incorporating that version into our system, then we will be able to take advantage of the GPU side of retro as well. So that's one advantage. Another thing is that I'm pretty sure now you've heard spectral element variable resolution grids. And I just put some examples here, but there are many, many examples of various uses of spectral element atmospheric model with variable resolution. And these are mostly community-driven efforts. And these versions are going consistently towards finer and finer resolution. The examples that are listed are over here, the 1/8 of a degree, but there are 1/16 of a degree versions, and people are planning to use even finer resolution versions. As we get to finer and finer resolution, then we are actually sort of pushing the boundaries of non-hydrostatic or hydrostatic assumption. An important application of the spectral element non-hydrostatic dynamical core will be essentially use of that dynamical core in variable resolution versions of the spectral element atmospheric component so that we can actually properly consider the associated physics in these applications. So I'll just show you some examples of where we are going with CESM3. And I just wanted to make sure, also make one thing clear. In the past, we provided sort of CESM releases. We had like CESM 2 release, CESM 2.1 release, CESM 2.2 release. But now everything is in the open. I mean, you can essentially go to GitHub and you can see what version of the model exists today. We don't have to have any sort of that many releases anymore. If you are interested in seeing what we are doing, the latest, but not necessarily the greatest versions of CESM, they are all available. So when I say towards CESM3, we will have a released version of CESM3 maybe next fall. I want to be careful with what I say here. But there will be other versions of CESM3 available. They may be 2.9, 2.99, 2.999, or something like that. But as we bring in different features or new capabilities, they'll be available to the community. For example, what we have two new capabilities, and I'm sure you heard about these. We have now SLIM, that's the Simple Land Interface model. It's implemented already as its own component and will be released soon, again on GitHub. We have, for example, gray radiation aquaplanet version of the model. It's already implemented. This slide is 1 month old. I'm not sure whether it's already released or not, but it was about to be released. Anyway, if not released, it will be soon. Another thing, probably Alper or somebody, I don't know whether mentioned or not, we are working on graphical user interface and tools to support CESM specialized and flexible model configurations. Right now, usually you create new case and blah, blah, as one-line arguments or whatever. But now we have actually prototype versions of a GUI interface. You do not need to use create new case. You can just essentially choose what you want to do and then click these things, and you can, a model version based on what you want to do will be automatically created for you. And this also does the checks. So for example, if you click on something, it'll tell you also what chemistry, what physics, or whatever options are available for each component. Then it is going to make sure that you are not doing something that you are not supposed to do. So it will be self-consistent. Prototype versions are being used by our sort of friendly users at this point, and it should be available pretty soon. We are also pursuing, and some of these are also, as I said, in the strategic plan, new technologies. And one of the things that we are actually looking towards is machine learning for whether worst, better or worst. I know that some people are against it, some people are embracing it fully. But there are certain advantages. For example, if you go to ultra-high resolution simulations, when you run it on GPU-based systems, thinking is that if you have ML-based parametrizations, that's the thinking, that needs to be proven and all that stuff, then it'll be a lot cheaper to run on GPU-based systems or more efficient. I suspect that the same is true on CPU-based systems as well. But what we are doing is essentially we are taking advantage of our external collaborators and LEAP project, M2 lines. There's an HPE supported project that's the Smart Sim, and then we have collaborations or at least interactions with NVIDIA. If you know what these are all, NVIDIA is a private company. And the others are, well, HPE. HPE is also a private company, but LEAP and M2 lines are NSF-funded. Yeah, M2 lines is also NSF-funded activity. We are also, like just an example, since I'm an ocean person, I just wanted to mention that our ocean model, you've used POP, that stands for Parallel Ocean Program, but in CSM3, we'll be using MOM. That's the Modular Ocean Model version 6 from GFDL. And we have already, we have 2/3 degree simulations already. That's the course resolution here. But we have created 1/4 degree, 1/12 degree, and 1/36 of a degree versions of the model. I should be careful. We have simulations with 1/4 degree and 1/12 of a degree, but we have no simulations available for 1/36 of a degree simulation yet. And yeah, so you can see one animation there. And where are we with respect to our workhorse CSM through configuration? We have actually started our initial evaluations of the coupled system. We are using MOM6 as the ocean component. You've been using CIS5. We are switching to CIS or going to CIS6. And you've been, we are also using new versions of the atmospheric model, CAM6 spectral element. The versions that you use right now have 32, I believe, vertical levels in the atmosphere. We are going to 92 vertical levels. So it's going to be quite high resolution, but initial workhorse configurations are using 58 vertical levels. We have done many, there are many new developments and features in all the component models. We have performed over 50 multi-decadal to multi-centennial simulations. We learned a lot. We found a lot of bugs. It's part of the sort of our experience. And unfortunately, so far, one of our old problems is back again. In our preliminary simulations, we are seeing actually a freezing of the Labrador Sea. And that results in shutdown or weakening of the Atlantic meridional overturning circulation. We had the same problem in CSM2. Unfortunately, at that time, despite our all efforts and spending a lot of time on it, we could not find a satisfactory answer. There was no silver bullet. In one case, it was something causing it. In another case, it was something else. So there was no actually satisfactory fix. And those are detailed in the manuscript that I led for CSM2, and we are in the same boat, it looks like, and many other groups are having similar issues. So with that, I'll stop and take questions.
All right. Thank you, Gökhan. So we have just a few minutes for questions. So if you have a question, can you raise your hand so I can get an idea of how many? Okay.
Thank you for that presentation. I was wondering if non-US students, if there's any way to access supercomputer resources or if not.
Well, my understanding is that no, right? Unless you are in collaboration with somebody. I don't know the details.
So 2 things on that. So one, I just did get word from Sizzle they'll extend all the training accounts till July 31st. But as for long-term access, I can check. So if you want to send me an email, I'll follow up with you. But I believe it tends to be for NSF-funded researchers. So you need some collaboration here or at a university in the US. Yeah.
Are you from UK?
Australia.
Australia, okay. I was going to say there's also a UK effort. The CSM is transported to, what is it? Archer 2.
I am a dual UK national, so maybe that would.
Yeah, you may access it from there as well.
Thank you.
CSM2 should be running on Archer 2 right now.
I didn't get to it because of this. Next week.
Next week, sorry, next week.
All right, are there other questions? I'm going to say just before this next one, with the accounts extended, please be respectful users. You all have access to this allocation. So if one of you uses up all the core hours, that's really rude. Don't do that. Okay.
Okay, thank you very much for this great presentation. I think it is very good, especially give an overview about all these activities. I am very optimistic with this model. And I am asking mainly related, my question mainly related to the strategic plan. Is it editable so I can add ideas or something like that?
Well, right now it is not editable because it was editable up to...
Or how to share my ideas with...
Yeah, I mean, so yeah, take a look at it. And then there is quite a bit of society relevant actionable science areas there. So, and you can send those, I mean, just send it to us and then...
Okay,
yeah.
sure. Okay.
Yeah.
And also I have an opinion. This is my opinion. Using of machine learning or artificial intelligence in climate systems is very complicated. Maybe these two components, maybe it could be valid for one axis or one component only, but include to be used in a very complicated system with different feedbacks, interactions, I have a big doubt that this could be done.
Yeah, I mean, that's a major research topic. There, as I said, there's the M2 lines and there's the LEAP project. They are actually developing like replacement for certain parameterizations and all that stuff, but how that whole thing interacts within a coupled system is going to be a major research topic. Yeah.
All right. Thank you so much, Gokhan. I'm glad you could wrap up because he's leaving again tomorrow, so we just caught him.
Questions or whatever, just send me an email. My email is my first name at ucar.edu.
Sure. Yeah, thank you.
All right. Okay, so we just have a few wrap-ups. So I just want to say thank you all for coming. One quick announcement. Someone asked me about stickers earlier. I went and asked Syed. They do not have any stickers, but they had these big posters. So if you want posters, there's a pile here with some rubber bands, and I'll just leave them here for you to take as you leave. It's the mural that's up in the hallway. I just had a few last kind of parting thoughts. So this is how I started the day. How do you feel? You might have started this way after yesterday's lab, but maybe you've moved more this way after today, I hope. I'm not sure, but even if you are feeling this way, that's okay. I just want to point out again, these were kind of the goals we started with. After attending the tutorial, we wanted you to have some foundational scientific understanding of the core CESM components and CESM features. We wanted you to be able to run and modify the model and use some of the output. We wanted to give you opportunities to network with peers and CESM scientists. We wanted you to get at least some understanding for the HPC needs for CESM, and we hope that you perceive this as an inclusive learning environment. So I think maybe where this comes from, actually, I have a friend who did a postdoc here, and she moved on to another modeling center I will not name, that does not have this community aspect that puts so much into documenting and trying to make it easy to use the model. And she told me it was like coming in and you go into a building and there are no lights and there might be holes in the floor and you have to find your way to like the third floor, someone's specific office, and there's no instructions, and it was really hard. So hopefully, and in contrast, CESM, hopefully it's like there's a maze and you have to get yourself to the center, and you might be at the point where there's like a little bit of light shining, but it's not completely dark still, or maybe the sun has come out and it's like all bright and sunny and clear. And what we've tried to do with all the documentation we do is also provide a map. And I think these are the things that really make CESM unique compared to many models. And we do put a lot of effort into them here. So I just wanted to point that out. You might not be at the center of the maze yet, and a lot of us who work here still feel like we're wandering sometimes. You go down a rabbit hole or whatever, but at least we're working together to figure out how to get whatever science we want to get done. So thank you for attending. You all, I want to point out, you all just should have received an email from me with a link to a survey. We've built in this last 30 minutes time time for you to fill the survey out, so you don't actually have to take the bus until 5. So we want you to stay in here, and we really would appreciate feedback, as I pointed out, what the learning goals were, how you felt like the week went. We're not trying to collect, I don't think you need your email address, so it's all anonymous, but we do look at these and we'll take it into account for future years. So hopefully you'll do that right now. It'll be open for another 2 weeks, so if you can't do it right this moment, that's okay. But that's kind of what this last half hour is intended for. Monica, you had a...
So I have some vintage
Oh,
stickers that have been back in my office.
vintage stickers.
They're the in-car climate data guide, but like totally give that some advertisement. So
Okay.
the
The climate data guide's in the website we put together. So I will put the posters on this side. I'll put the stickers on this one. And Syed was like, oh yeah, we should make stickers that we can give out. So I think that's all. Are there any final questions or comments? Thanks. Yeah, thanks.
Well, yeah, I mean, I just wanted to really acknowledge the great work that has been essentially undertaken by Alice and all the Peter and who else was on the CSM tutorial, and especially the person who is sitting here, Elizabeth Faircloth, and they have done a tremendous job. And this takes a lot of effort, going all the way back to, I don't know, December or November, trying to sort of get the applications going, and then reviewing. I think that you guys received, a record number of applications, over 200 applications. And then there's the writing of the proposals and all that stuff to get this effort funding. And I mean, and then like last minute, my flight gets canceled and Alice is in like, what do we do and all that stuff. It's just, so I just wanted to make sure that we give a round of applause for that.
All right, so I'm going to leave the room while you do the tutorial, or while you do the survey. I think all the NCAR staff is going to leave so that you can fill it out without undue, whatever, pressure, whatever they say. So anyway, thank you. We really do appreciate that. And hopefully you'll be in touch, and we'll see you at working group meetings or the annual workshop.